Okay, plan for today. We'll talk about comparable and compare-to methods first. In the first maybe 20 minutes to 30 minutes, for the remaining part, I'll start the topics about hashing, hash table, especially how you can write a hash code. Writing the hash code method as you did for lab number 2 itself is quite easy, but I'll rather give you the complete story about why hash code can be useful, especially put it in the context where about runtime performance, right? Hash code is really a good way to improve your performance for overall. But I'll give you the complete story after the comparable. Okay, let's review this motivating example very quickly. Okay, every time if you got a list of records you would like to present or want to sort, and you can definitely use the arrays class in the Java library, and they have a sort method. But in order to use that particular library method, you have to define what does it really mean for my object to be smaller than the other. Okay, that's kind of the idea for compare to and comparable. Okay, let's just see the motivating example and see how we can program that in Java. First of all, you can see that we got this particular small simplified database over here. So we got name, we got ID, unique ID, and also got salary for each employee. And then let's say we got Alan, Mark, and Tom. We got 3 rows to consider. So let's say we want to generate an annual report for the employees. So there are different ways you can sort the employees accordingly in the report. One way to do it is you can simply just sort based on their IDs. In this case, you can see Tom's ID is the smallest one, so Tom goes first. So that's why you see Tom is over here. And then the next one will be Alan, the second one. So Alan will be the second one. And also the third one will be Mark over here. That's why I got this order here. One thing I want to draw to your attention over here. You can see this particular list is sorted according to the ID, right? But something I would like to draw your attention here. You can see that the reason that Tom appears before Alan over here is simply because the ID of Tom is smaller than Alan. Okay? However, what if we want to sort in the opposite way? We want to say maybe the ID that is the largest should really come the first. Okay? Maybe we want to do the reverse order. Let's say alternatively, if you simply want to do the following, you want to say Mark, Alan, and then followed by Tom. In this case, you can see Mark's ID is 3, and then Alan's ID is 2, and then 1. So 3, 2, and 1. In this case, you can see Mark's ID is the largest, but Mark himself is considered as the first element in the sorted list. So that means Mark is considered as the smallest element in the list. That's something we're going to play with. Okay? Now, one more example here. Let's say we want to do a more sophisticated mechanism of sorting. What we can do is we're going to say, let's sort by salaries first. If the salaries are higher, then that person should come earlier in the list. If 2 employees have the same salary, and then we're going to sort based on their ID. Okay, just the 2 criteria over here. So in this case, you can see that the largest salary is simply over here is Alan. So this is the largest amount. Okay, so that's why Alan comes first. Okay, and then you can see that Mark and Tom, they actually got the same salary. So that means based on the salary, we cannot tell which one should really come first. In this case, we compare their ID as before, 3 and 1. That is why you can see Tom should really come first before Mark over here, right? So based on the 2 criteria, we can sort the employees in a different way. Now we want to see exactly how you can program this in Java. So in Java, you can decide, you can customize the way you want to sort the objects. You can define the criteria yourself. Let's see examples. Okay? So now what I want to do is I'll show you the code example right away. Okay? One more thing to note. Okay? If you see the sorted list over here, I'll give you one example. Can we just consider this list again? So let's say this is sorted list number 1, and this is sorted list number 2. Okay? Let me just write it out explicitly and mention one more concept to you, and then we can go to Java code. For list number 1, you have Tom, followed by Alan, followed by Mark. On the other hand, for list number 2, you have Alan, followed by Tom, followed by Mark. Okay? The way you read the list is from left to right. In this case, I want you to look at the leftmost item in the list is considered as the smallest objects. I'll just put it here. What do I mean by smallest? I'll put it in quote. Smallest objects in the list. That's the leftmost. So based on criteria number 1, just based on ID, Tom is considered as the smallest because Tom's ID is the smallest. But based on our criteria number 2, Alan is considered as the smallest in the sense that, I know this the thing is a little bit not so intuitive here. Let me try to say this, the second one. Alan is considered as the smallest objects, so Alan should really appear as the first element in the list. It's always sorting, let's say, in the ascending order. However, we say that whoever who got the largest salary should come before whoever got smaller salary, right? So that means Alan, who actually got the most salary, the highest salary, should actually come as the smallest elements in the list. Okay? So now you can see that apparently you can see, are we really contradicting ourselves? When you talk about highest salary, but on the other hand, Alan is considered as smallest in the list. That's something I want you to get through, hopefully by the end of the lecture. Okay? It's completely up to how we want to define the ordering between the objects. Okay? Okay, let's see example right away. And then let's see how we can program that in Java. Let's talk about the criteria number 1. How do we sort just by ID? Okay, how do we do that? All you gotta do is as follows. You have to use increments. So let's say I want to make the employee class, let's say comparable. I simply put the C over here, just standing for comparable. And then 1 here is for version 1. We're using criteria 1, just using the ID. Okay. First of all, you gotta say increments over here. We'll talk about increments a little bit later when we talk about interface. For now, you simply can remember that whenever you want to make your class comparable, this is all you got to do, just say increments. So I wouldn't test you on this for the syntax just yet. Okay, so you just have to know how to use it. So we're going to say this particular class increments, and then we have another class called comparable. Okay, that's how you use it. And then over here, you got the angle brackets over here. Okay, you just have to repeat the class name again, just how you use it. Okay, so this part over here for angle brackets is something called generic parameter, and this is also something we'll talk about a little bit later in the course once we talk about inheritance. Okay, for now you just have to know how to use it. We'll talk about the rationale behind using the interface and generic parameter a little bit later. Okay, as soon as you implement the comparable, there's only one method you're obliged to implement, which you already did for lab number 2. Let's just go over that for this simple case. So the method is called compareTo. Okay, it's going to return some integer. Okay, and then the object type is going to be the same as the class we are currently talking about. Okay, and then it's going to be some integer expression over here, just an integer expression. So here comes the rule. Okay, over here I'm going to write it here. If the return value is less than 0, or it can be equal to 0, let me just say less than 0, or it can be larger than 0, or it can be equals to 0. Okay, so these are the only 3 outcomes. When I say less than 0, you can return just any negative number. It can be -1, it can be -2, any negative number. Okay, if the value is exactly equal to 0, that means you're considering these 2 objects as the same. No one is larger and no one is smaller. Okay, let's see for this particular example. When I say this.id minus e.id, basically, right? Okay, let's just try to go over some code over here, and then we'll see how things will work. Okay, let's just apparently you can see this one is going to return a integer expression. Let's see some example right away. You can remind ourselves over here we got Alan, Mark, and Tom. For Alan, he has got the ID 2, and Mark 3, and Tom 1. Let's do the compareTo right away. Okay, let's try the following. If I say Alan dot compareTo, and then I can say Mark over here. Okay, if you try to see this particular call, what should be the result over here? Just trace the code and tell me. -1 because Alan here is this. This.id is Alan.id, which is 2. And then Mark is basically the argument E over here. So E.id should be replaced by Mark.id, which is 3. So you got 2 minus 3, right? So in this case, you got -1. As I said before, here, when you say Alan compared to Mark, you get -1, some negative value. Conceptually, what does that mean? I'm saying that Alan is smaller than Mark. As far as the current comparison criteria is concerned, we are only comparing by ID. Because Alan's ID is strictly smaller than Mark's ID. So Alan should be considered as smaller. Okay, let's do one more. How about that? Let's do also Tom. What about I do Tom dot compare to? Tom dot compare to, let's say, Alan. So what would you get in this case? If you say Tom dot compare to, again, what's Tom.id in this case? Tom.id is 1. Agree? It's 1 over here. What about Alan.id in this case? Alan.id is 2. So you got 1 and 2. Again, you get -1. This will also return -1. I'm just tracing the code. Okay? So now how do we interpret this result? When we say Tom.compare to Alan, we get a negative number. So that means conceptually we get Tom is less than Alan. Okay? Now I want you to look at these two mini remarks over here. When I say Alan less than Mark, and also Tom less than Alan, what can I conclude from there? Basically, I do have some order, right, of the list. I do have to say Tom. So that means if I combine these two together, what I got is I got Tom less than Alan and less than Mark. That's what I get. That's exactly how I got the list over here. Tom, Alan, and Mark, according to the first criterion. Okay? Now one more thing to show you. Okay? Before I just give you another small change to the code. Okay? Okay, we also set the salaries, but we don't care about the salary for this particular version 1. Okay? And then we simply got an array. You can see this primitive array with Alan, Mark, and Tom. And now this is where the compare to can be useful. You simply call the arrays class, which is defined in the Java API, and there's a method called sort. In order to use the sort, you have to pass an array of comparable objects. That is why we did comparable over here for the employee. Okay? So after this, they will give us exactly Tom, Alan, and Mark. Exactly this order over here. So what I try to explain to you over here about Alan less than Mark and also Tom less than Alan, that's exactly what a sort method will do when they try to compare. So what's really important over here is over here. Okay, just return. So now let me give you one strengthening concept exercise. Okay, as you can see currently, the way I order the 3 employees, I say if the ID is smaller, they should come first. Let's flip it. I want to say if the ID is greater, then they should come first. Which means, now my question to you, let's say the test code over there, the JUnit test, I don't want it to change, okay? What I want to have eventually is something like this. Let me put it in green. This is the only line I want to change. I wanted to sort the array so that I got Mark, Alan, and Tom. So let's say this is a new expected list. Okay, let me give you a little bit hints over here. If I am expecting this green list over here, what does that mean? That means I want to get the following relation. I want to get Mark is less than Alan, and also Alan is less than Tom. That's what I would like to get. I want you to compare the green one versus the blue one over here. Okay? They're basically the opposite. Okay, the relations. How can we reverse this relation here? Like what used to be less than is now greater than. A hint to you, I can simply just change this compare to method here a little bit. Okay, anyone want to express your thoughts? how can I change the return value in the compareTo so that we can get this green list over here? Yes, please. Yeah, that's one way to go. Yes, why don't we try that? Okay, one suggestion would be, that's slightly different from what I expected, but that's okay, that's also work. So what you suggested was something like this. So rather than having this, I'm gonna say, I'll put it here. I'm gonna say return e.id minus this.id. Okay, let's see what's the consequence of doing this. Let's see exactly what's gonna happen. I would like to do the same exercise as before again. Now, if I say Alan dot compare to Mark, what would I get? I used to get -1, which means used to be Alan is less than Mark. What about now? I'm gonna get return e.id. In this case, Mark is e, right? So that means Mark.id minus, in this case, Alan is this, right? Minus Alan.id. In this case, Mark.id 3 minus 2. I'll get exactly just 1. So how do we interpret this? That means Mark somehow is larger than Alan. That's what I meant. Which is exactly the opposite to what we had before. Used to be, oh, the same. Am I doing something wrong over here? If you got, let me just do it again. Mark is 3 minus 2. I hope I'm not doing something wrong. Let's trace it again, all right? So got e. Alan is larger than Mark, right? No, actually, if you say Mark.id minus Alan would be positive in this case, right? Let me just make sure I'm saying this correctly. So if I say, let me just write this down, okay? Let me start from scratch so I don't really confuse you. Let me do it again. If I say Alan dot compare to, and then I have Mark. Okay, there's a new version, right? So what we will get is, we should really return this e.id and this.id, okay? In this case, Mark's ID is actually, over here, Mark's.id is 3. And Alan's ID is 2 over here. Okay, that's what we have, right? So that means e.id will still be 3 minus 2. That will be 1. Okay, so far so good? Okay, now so far so good. So the conclusion we can draw is as follows. Since I know, when I say Alan.compare to Mark, I got 1. So that means Alan conceptually is larger than Mark. Are you okay with that? I think I just drew the conclusion wrongly. Sorry about that. Okay, let's do one more. Okay, just to strengthen. Let's do one more. Let's say over here, we used to check to see what about Tom versus Alan. Let's say Tom dot compare to Alan. Okay, let's see what we have over here. Okay, so now in this case, Alan is basically the E over here. Alan.id is 2. So we got exactly 2 in this case. Okay, and then what about this? This is Tom. Tom.id is simply just 1. Okay, so 2 minus 1 in this case. So 2 minus 1, we get exactly just 1. So now what does that mean? Exactly, that means Tom is larger than Alan. Let me write it down. So that means Tom is larger than Alan. So once we get these two red relationships over here, you can see it's exactly the opposite to the 2 blue ones before, right? So what we can draw the conclusion from here is you just get Alan larger than Mark, and then larger than, and also we got Tom here as well. Tom larger than Alan, larger than Mark. Okay, that's exactly how you get a revert list. Okay. Guys, any question about this? I know it's a little bit confusing here, but let me recap what I have just done. Okay, this is something you're expected to try to work it out on paper first. So you can see, as soon as you change the definition for compareTo, you're basically defining the relationship between any two objects to see which one's smaller and which one's bigger. The smallest one always appear to the leftmost position in the list after sorting. Okay? Any question here before I talk about the second part, which is slightly more complicated? Yes?
This compareTo method only compares the ID number, right?
Yes, exactly. So version 1, we are doing something simple, just compare the ID. Apparently you can see the blue part, I simply say this.id minus e.id, right? Just to see which one is smaller. But if I flip the way I do the subtraction over here, you can see the order for the resulting list will be reversed. Okay? So what I would suggest you do is, I'm going to make the source code available to you, and then what you can do is as follows. When you run this test over here, run it first. This test is going to pass the first time. But now, if you make the changes as you suggested, to say the following. As soon as you say return e.id minus this.id instead, the test is going to fail. Simply because now the list will be reversed to be expected rather than the original one. Okay? That's how you play with the compareTo. Questions about this? Are we okay? Okay. How about we do a second example? Questions, yes.
Kind of general about JUnit test, not about this one specifically. When you're making a JUnit test, the latest test that you make, like not the first one, talking about the last one, it's going to have more of those, I mean, it has a copy of all the tests, right? Not the copy of the test itself, I mean, if any method has been implemented, if a new class has been like initiated or something like that, so I mean, the amount of information that you have in your test, they would add up when you have more tests.
Exactly, yeah. So you can think about every time, this is about test-driven development, regression test. So every time when you are developing new tests, they will simply be accumulated so that if there's any new change you introduce to your software, they will be rerun to make sure everything is okay. Otherwise, you shouldn't continue to develop your code. Yes?
Where did you call the compareTo method?
Good question. The question is, where do you call the compareTo? The answer is as follows. You can see I'm trying to call the compareTo explicitly for you to illustrate for you, right? You can see over here, I can see Alan.compareTo and Tom.compareTo. You don't really see this exactly in the Java code, simply because the library class over here, arrays.sort, it does call that internally. Okay? So you can see that basically the way they do the sorting, which you will learn maybe in 2011, is something called merge sort, but you don't have to know for now. But this line over here internally is going to call whatever compareTo you define for your employee class. If you do it the old way, we're going to get Tom followed by Alan followed by Mark. If you change it to be this reversed subtraction over here, the expected list will be reversed as well, right? So as soon as you change the compareTo, the way they do the sorting will also be different. Okay.
In this example, we have only 3 elements, but what if we have like 4 or 5?
Doesn't matter. If you have a million elements, they will still do the sorting accordingly. You can think about they will just do some pairwise comparison of every elements, and then they will figure out exactly who should be the smallest and who should be the largest.
What I mean is like there will be too much possibilities of comparing.
Oh, you're talking about how exactly we do the sort, right?
Yeah.
So we'll talk about some very naive ways of sorting, namely insertion sort and selection sort. We'll talk about it maybe after reading week, especially we're going to compare their performance. Okay, the merge sort I just talked about got very reasonable performance, but it's too complicated to talk about in this course, but you will learn about it in 2011. Okay, but I like this question here. The main concern is, what if you got a very big list, let's say with a million elements over there? How do we do the sorting efficiently? We do have certain algorithm for supporting that, but we'll mention that, as I mentioned, you'll learn about them. You had to implement those as well in 2011. Okay, not this course. Yes.
So when it compares to, how do you determine that the number is positive, bad?
Okay, so basically the question was, if I really, okay, So if you compare the two different versions, the first version was this return this.id minus e.id. That's version number 1, right? And then the second version was e.id minus this.id, right? So these are the two versions. The convention is simple. If the return value from this particular, let me be consistent with color here. If the return value for this particular integer expression here happens to be less than 0, that means, for example, the context object over here for Alan is the smaller one. That's why we get Alan smaller than Mark. As soon as you flip it, it's going to change the sign, right? Let's say 3 minus 4 is minus 1, but 4 minus 3, if you flip it, will be you change the sign, right? So you're going to flip it, yeah. Okay. Okay, let's now see another example over here. So this one here is a little bit more sophisticated. We want to say, let's compare salaries first. If the salaries for the employees are the same, then we will bother to compare the IDs. Okay, salary first and then the ID. Okay, so now let's have a look at how the compareTo method is defined over here. 2.1 is version 1. Okay, so I'll show you two working versions. How about we look at version number 2 first? Version number 2 might be slightly easier to understand. And then we can see how it can be simplified to version number 1. Okay, how about we do that order? Okay, let's say we do it over here. Okay, let's say we got version number 2. So you can see C, comparable employee, number 2. Also increments, comparable, and also put a class name over here. Okay. So now let's see how we define the compareTo objects over here. Okay, think about the comparison mechanism over here, right? See, so if you look back here, let's look at this table here. We're going to compare, first of all, the larger the salary is for the employee, the earlier they should occur in the list, right? Which means somehow the salary, if employee got larger salary, they should be considered as smaller in the list. So they will appear earlier in the list. Okay, first of all, let me write it. Larger salary, let's see how the logic will work. Larger salary means occur earlier in the sorted list. And any element that occurs earlier, that means they're smaller, right? Only the smaller one actually come before the larger one. They are considered as smaller. Okay, we'll run some example in just a moment. Okay, consider small. That's really the most tricky logic you have to go through. Okay, so now you have to think about which one should occur earlier in the list, which one should appear more to the left. On the other hand, which one should be considered smaller. Okay, that's the kind of logic. But let's see how things can be defined over here. Let's just go over the code. Okay, now let's have a look at this line here. I say if this the salary strictly larger than other the salary. For example, Alan's salary is more than Mark's salary. That means Alan should appear earlier than Mark. So I simply just return a negative number, making sure whoever got the higher salary, they will get smaller. So they'll be put more to the front of the list. Okay? And now, on the other hand, this the salary and other the salary, if it's the other way. If I got smaller salary than the other, I should appear later than they are, right? So I should be considered bigger, in the list. So that's why you get a positive number over here. We'll do one example in just a moment, but let me just go through the code. So now, what about the else part? You can see the if part and the else if part. We talk about whether the cases where the salaries are unequal. If they are equal, then we compare the ID. In this case, we go back to our old logic over here, right? I simply say this.id minus other.id. Okay? Let's see how things can work. Okay? What I would do is, let's see how exactly things can work. Let's remind ourselves and do one example for our 3 employees. So we have Alan, we have Mark, we have Tom. Okay? Let's remember that Alan has got the largest salary, which is over here. So Alan's salary is this much. On the other hand, you can see Mark's salary is just the same as the salary for Tom. So they're the same. Okay, why don't we try this? Let's try the following. If I try Alan dot compare to, and then I would say Mark. What would that be? Alan dot compare to Mark. Why don't we try to trace? Alan apparently would be this, right? So I'm talking about this would be Alan. Alan dot salary. In which case, that would be this amount. What about other? Other in this case would be Mark. Other dot salary would be this much. Apparently, we're going to satisfy this particular branch, right? And then we're going to return -1. Okay? It's going to return -1. So what does that tell us conceptually? That means over here, let's draw the conclusion over here. Alan is considered as smaller than Mark. Okay? So far so good? Why don't we do a similar comparison just for clarity? What about if I say Alan dot compare to? And I will compare with Tom in this case. Well, in this case, again, we're hitting this particular if branch over here. Alan, the salary is this much, and Tom, the salary is this much, the same as before, right? It's Mark. In this case, what we'll get is, again, -1. That's what we'll return, right? So we'll also get -1. So what does that mean? That means conceptually, Alan is also smaller than Tom. Based on these two, what does that tell us? Alan is considered as the smallest among the 3 employees. So that means when you talk about a sorted list, Alan should appear to the leftmost. Okay, so far so good? Yes, question?
The type of returns that we have here, -1, 1,
Yeah.
and +1,
Yeah.
are these things that are needed by the array sort?
Correct. So more precisely, that's a good question. You can see the value we are returning here, the exact number here is not important. The sign is important. Whether that's negative, 0 or positive, these are what matter. That's why for version number 1 here, we just stick to, for this particular 2.2 version, we stick to -1, 1, and 0 just to make it clear for you. But you will see to simplify this logic a little bit, the 2.1 will be slightly better. Okay, we'll see. Okay, any question about this? Okay, let's do one more comparison, shall we? Let's do one more over here. What I can do over here is I can say, what about compare Mark and Tom? If I say Mark over here dot compare to and Tom. So this case will be a little bit more interesting. Okay? So now in this case, you can see Mark will be this. And Tom will be the other. Okay? So now, what about the if branch over here? The if branch, we say this the salary, which is the salary for Mark, which is over here. And then what about other the salary, which will be the salary for Tom, in which case that's the same number. So we don't hit that, right? So this branch doesn't satisfy. Similarly, the else if also doesn't satisfy. So we go to the else branch directly. Now for the else branch, we basically don't worry about salaries anymore since they are just equal between Mark and Tom. So what do we compare right now? We simply say return this.id minus other.id, which would be mark.id minus tom.id. Okay? In this case, mark.id would be 3. And tom.id would be 1. So we get 3 minus 1. So we get -2. You can see it doesn't have to be -1 always. Okay? As long the sign is more important. So now, how do we judge this case? How do we interpret this? Do we say Mark is smaller than Tom or the other way? Mark is smaller than Tom, right? So when you say something dot compared to something else, the sign tells you exactly how you should interpret that, right? So now, Mark is, did I say, Mark is 3 minus 1. 3 minus 1 is 2, right? Not minus 2. Yeah, okay. I just did it wrong. It should be 2. Yes. So mark the ID is 3 minus 1. You're exactly right. I'm not sure why I said minus 2. Okay, so it should be 2. So that means conceptually, we got mark exactly. Is that right? Mark the ID is 3, and minus other.id is Tom.id, which will be 1. So we get 3 minus 1, so we get 2. So that means Mark should be strictly larger than Tom. Okay, questions until here? Are we okay so far? Okay, so what do we know from this? What we know from this is, once we know about these 3 relations over here, so what I'm talking about right now, I'm trying to do the pairwise comparison using compareTo for you. But these are the things you don't have to worry usually when you simply just call arrays.sort. So this will be done automatically for you. But you have to know individually how you compare the elements so that you can define that compareTo properly. Okay? So once you do that, you will see exactly what you expect. Okay? So now, this basically just corresponds to what we said in the beginning. How do we sort based on their salaries and ID? Okay? Over here. Guys, any question about 2.2 version here? Okay? That's one way of writing it. Okay? So you can see another version over here. There's another version. Let's have a look, which is briefer over here. This is just another version, which will do exactly the same thing. Let's see exactly how that can work. So we basically, again, we got this compareTo method to define because we implement from comparable. Okay? And then we simply just define some difference between the salary. Okay? And also we got some difference between the ID. We got 2 variables to show you. Okay? And then the ID diff is simply just the same as before. So that's no question about it. So over here, I'm just reusing some library method again for you. So the double class is like an integer class. They have simply a method called compare. I'm just showing you how you can use the library method. Okay? They are simply going to compare this.salary versus other.salary. Okay? So it's going to return to you again is either minus or positive or 0, right? And then once you combine, once you see over here, we have an if then else logic over here. We say that if the salary is different, which means the difference between the 2 salaries is not 0. In this case, we simply just return the difference between the salary. I'll come back here in just a moment to see why we need a minus sign over here. Okay? Otherwise, if the salary is the same, we simply return what's the difference between the ID. Okay? So now the tricky part really is here. So why do we need this minus over here? Why do we need it? Yeah, you want to try to explain to us?
We said the highest salary is the smallest.
Aha, okay. Why don't we just do one example? Exactly. Think about it this way. Okay, let's just use an example to convince us. Why don't I take Alan and also Mark over here? Okay? Alan and Mark. We know that Alan should really appear before Mark in the list, right? Alan should really appear before Mark. So that means Alan is considered as smaller than Mark conceptually. That's what we know. However, here when we talk about salary difference, when I say double, let me just put it here. When I say double dot compare, okay, so over here I say this dot salary. Let's say over here Alan dot salary, and then I will put Mark dot salary. Okay, let's get these two. Okay, let's see what we get. Alan's salary is simply this big number over here, 4,500. And also, Mark's salary will be this 3,450, right? If you try to compare what's the difference between them, what would you get? Would you get some positive or negative? Just compare. Well, you get simply just a positive number. Okay? However, if you use directly this positive number over here, that means you're comparing, you're basically saying that you're basically saying Alan is larger than mark. That is not right, because larger should appear later in the list. In this case, that's why we should flip the sign to be minus. That's why you see the minus over here. Okay, let me just put a note for you. Without this minus, without this, Alan will appear later than Mark in the list. Okay, so version 1 and version 2, which one to use is completely up to you. Okay, but we're just encoding the logic over here. So you can see the way we do the comparison here, the sign is really important, either negative or positive. Okay, okay, questions about this, compare to. Okay, no questions? Oh, okay, good. All right, let's see over here. Okay, let me just see if there's any more slides to go over for, but all the slides are things I've already covered in the example, so you can just go through them. Everything has been set already. Okay, let's see. Again, so this is something you should really keep in mind. So this is the only principle for you to actually program the compare to method. If it's positive, that means something is greater than the other. Okay, otherwise you got different sign. Okay, okay, you can go over them, and then I think I have talked about all the examples already. So now we can move on to hashing. Oh, just more property to tell you over here. So this is just a guiding principle for programming compare to. Okay, just in general. Let's say over here, so what, just say the first one. The first one over here, we're simply trying to say, you cannot have C1 less than C2 and C2 less than C1 at the same time. So it should be exactly just one of them should occur. Okay, that's something you cannot have. You cannot say Alan is less than Mark, and Mark is less than Alan at the same time. So that's something you have to be careful when you define your compare to. And also transitive. Transitive is also important. You want to make sure whenever I say Alan less than Mark, and Mark less than Tom, so that should mean Alan should be less than Tom as well. Okay? So based on these two principles, I would like to ask you this. Okay? Let's say we have a player for the rock, paper, scissors game. So each player can either have rock, paper, or scissors, the three different values. So now, is it possible to define a compare to method for rock, paper, scissors player? Okay, guys, do you know what the question is? You know rock, paper, scissors, right? So we know that rock is bigger than scissors, for example, right? So now let's say each player has either rock, paper, or scissors, three possible values, let's say. So now, how would you define the compare to? Let's say let's say the player for rock, paper, scissors implements a comparable. And now, is it possible to define the compare to method for rock, paper, scissors player? Is it possible? Is it going to violate any of the principle I just said above? Symmetric?
Asymmetric. It violates asymmetric.
Why would it violate? Well, let's say if I say rock is larger than Caesar, but we didn't say Caesar is also larger than rock, so that's okay, right? That's according to the rule. Anyone want to try the transitive over here? So asymmetric property is okay as far as the game is concerned. What about transitive? If I want to define the compare to for rock, paper, scissors player, is it going to violate the transitivity property? Is it going to? Anyone want to explain to the class rather than me? Anyone? Want to try? Nobody? You want to try? Or? Okay, yes, go ahead.
Rock is bigger than scissor,
Uh-huh.
and scissor is bigger than paper, but you can't say rock is bigger than paper.
Exactly.
Paper is bigger than rock.
Exactly. Let me make it very obvious to everybody, but that's exactly correct. So now, we know that rock is larger than Caesar, okay? Caesar is larger than paper. By transitivity, that means rock is larger than paper. Apparently, that's wrong for the rock, paper, scissors game. So this violates the transitivity property. So you cannot define the compareTo method for this particular application. Just not comparable. Okay? So later on, if I give you another example and I ask you, is it possible even to define a compareTo method? How do you decide? How do you judge? Basically, you have to rely on these two principles over here. Okay? These two. Both asymmetric, to see if that might be violated, or transitivity. Okay, so these are the two guiding principles. Okay? Okay, any question about the last example for comparable, rock, paper, scissors? Okay, if no question here, then we will talk about the hashing. Okay? Okay, it's a different topic. I would say for the compareTo, if you really find it confusing, that's normal, because the way you define the order is completely up to you, and you should know the consequence of defining a particular compareTo. Go over the lecture and then try to play with the code. That's the best way to clarify also by yourself. Okay, so now let's talk about new topic. So we're gonna, basically this is a roadmap for this lecture. We may not be finishing today, but definitely we're gonna finish on Wednesday before the reading week. The hashing mechanism is going to solve a particular problem, and the problem we are talking about is called a map. So let's talk about what a map is. It's a very simple concept. Maybe you have used that in your daily basis. Let's talk about what a map is, and then we'll talk about how you can have a naive implementation for map using just a single array, basically what you're required to do for the coming lab test 1. So it might be a nice review as well for this afternoon. Okay, we'll do that. And then we're going to criticize about this one array implementation for the map to see exactly the runtime performance that one of you guys is worried about. And then we'll see that the performance by just one single array is extremely poor. Okay? And we're going to talk about how you can resolve this issue by using something called hashing. Okay? And then we'll go into how you can implement in Java. Okay? That's basically the roadmap for today and Wednesday. But let's go step by step. First of all, let's understand what a map is. A map, basically, the people also refer to a table or dictionary. So map, table, or dictionary. Either one is fine. It's going to store a collection of entries. You can think about collection as something without any order. Okay? When you talk about array, you talk about first position, second position, there's an order. But for collection, there's no ordering. Okay? Entries. Let's define what an entry is. Let's see one example here. I'm not too sure if any one of you is still using this kind of old school style of managing your files. Basically, each paper folder over here is identified by some label. For example, Q2 report, right? That's a label. And once you find out what the label you're looking for, you can go inside the folder and find out the file. That's kind of the value you're looking for. That's one way to see it. Or let's make it more concrete. This is how you can think about a map. A map is simply a collection of entries. Each entry has two parts. The first part is called key, or sometimes we call search key. The reason that we call it search key was because the key is the only way for you to uniquely identify a particular entry in the map. Okay? That's why it's called search key. And each search key has an associated value. In this case, I simply say the search key is just an integer value. And then the value over here is simply a string or character. Okay? Just make it simple. Right, over here, I simply got 1, 2, 3, 4, 5, 6, 7, just 7 entries. So that'll be enough for our discussion. Okay? So we got a map with 7 entries. Questions?
So basically like the birthday book, we just go through in our...
Yep. For birthday book, you can think about birthday book is also a map where we are trying to use people's name as the keys and the associated birthday as the values. So each entry consists of the name and the birthday. That's another way to think of it. Yes. Okay, each entry has a value and the search key. Okay? And one thing to note, you can notice that over here, the search key over here, there's no duplicates, right? You can see 1, 25, 3, 14, 6, 39, 7. There's no duplicates. Okay? The search key, since it's going to be used for search purpose, if there's any duplicates, you wouldn't know which value to look for. So they must be unique. On the other hand, if you look at the values over here, you can see the C over here appear more than once. That's okay. Values can be duplicated, but not the keys. Okay? Conceptually. Okay, each search key must uniquely identified, so that's why they cannot be any duplicates. And now should be used to efficiently retrieve the associated value. So here, when I say efficiently, I'm not being very formal here, but I'll give you some intuition. So once we start talking about the so-called big O notation, so we'll talk mathematically speaking how we can analyze the running time for your method. So we'll get there a little bit more formally after reading week. But when I say efficiently, I'll give you more intuition as we go through the example. Okay, search key must be unique, as we said. Do not contain any duplicates. So now let's try to strengthen your understanding or intuition about map using something you're very familiar with already. Basically arrays, one-dimensional array, you can consider them as a map. For example, before I get there, let's get some intuition. Okay, before I even get there. Let's say this. If I have a string array, let's say simply just names. Again, let me just put Alan, Mark, and Mark. How about that? Apparently we got some duplicate names over there. And now let's try to see how we can relate array, which you're very familiar with already, to a map. Apparently, let's see, remember each map has entries. Each map has entries. Each entry has two parts. They got the keys and the values. So now, how do we relate arrays into map? Let's find out what the values are, in this case, of the array, and what the keys are. Okay? Can Alan, Mark, and Mark be the keys? No, they are duplicates. So why don't we just make them the values? Okay? Basically, values are simply just elements of the array. And of course, you can see it can be different type. It can be entry type, it can be person type, it can be point type, any type. Okay? What about the keys over here? Indices. Why do you think indices can be keys? They're unique, all right? And also we talk about efficiency, right? Okay, let's see how efficient they are. Okay, the keys are simply the indices. In this case, what are the keys values? In this case, it will be 0, 1, and 2. Given the key, I can uniquely identify the corresponding elements over here, right? And also given 1, I can know it's exactly this mark I'm talking about, but not the other one. Okay? Just about the efficiency. I believe you learn much more in 2031, but I'll mention very quickly, okay? So now, let's say if we got an array like this, A pointing to, let's say, 3 elements over here, 0, 1, and 2, okay? And then we got Alan here, and we got Mark here, and we got Mark over here. How do I refer to this Alan here? The way, I cannot simply just say A. You can think about A is pointing to the beginning address of the array. Okay, pretty much consistent with how we understand reference type. Okay, beginning address of the array. Okay, now what about A0 versus A1? So now when I talk about efficiency, basically when we talk about computer memory, the way array stores information is very similar to how you organize the memory, just byte after byte. Okay, so now in this case, given that A is already the beginning address of the array, when I say A0, I simply mean go there, go to the beginning address directly. You can find out Alan without any offset. So you can think about the index over here is simply some offset units. Okay, just go there directly. Okay, on the other hand, what happens when we put 1 over here? 1 simply means you cannot just go to the beginning of the array. You have to somehow go to some later address. In this case, Mark should be over here. So that means between the beginning of the array and the second elements of the array, there's certain offset over here for the address. Okay, that's what the 1 over here really means. So 1 unit of offset depending on what the type is. Okay, anyway, that's all I want to say. Just go to the address with 1 units of offset. Okay, you will learn more about this kind of pointer arithmetic in 2031. So just maybe pay more attention to it when you get to 2031. Okay. Anyway, so that's about the array. Again, the indices can be the keys. And also whatever elements we're storing will be the values, right? Apparently, you can see the values can be duplicated. On the other hand, the indices must be unique. Okay? And then the way we retrieve the elements from the array is also very efficient, just based on calculation of the address. Okay? That's about what this slide is saying. Okay? Each array entry is a pair. Okay, you can go over that. That's exactly what I said. Any question about connecting array into a map? Hopefully you can see the connection here, right? Just one example for the map. Numerical indices are the keys. Also, whatever object is stored in the array, they are the values. Okay, here are just more examples over here. In the case of the array, the keys are simply just numbers, but they don't have to be numbers. They can be any types, okay? For example, let's say your student ID can be the key, right? Given your student ID, maybe it's a string, I can get your student record objects, right? Similarly, if I given a social security number, that also can be a key, right? No two persons have the same social security number. I can get your resident record, etc. Another one would be interesting is, you remember, I'm not sure if you noticed that every laptop or machine you're using, they got something called MAC address, the physical address. That's also unique. So given the physical address, we can also identify what your machine is. Similar idea. That's also the map for concept for the map, also for web page. Okay, so now we got an intuition about what a map is. Let's see exactly how we can implement a map. Let's talk about a naive implementation, okay, using a one-dimensional array, and then we'll criticize about it, like how bad it is. Okay, the way I'm going to do this is, let's say we want to just construct a map like this with 1, 2, 3, 4, 5, 6, 7 entries. Let's see how we can do that, and then we'll see how inefficient it might be in order to search for a particular entry, given a key. Okay? Why don't we have a look? Let's see the naive solution. I will just show you very quickly on the iPad, like how things can be done. Okay, let's say this. Again, so this is our database over here, and let's say the first item we want to insert will be with a key 1 and also value D. Okay, how do we do that? Okay, as you have been very familiar with, the way we program this is by declaring an array like this, and let's say we have up to 100 different entries, up to, let's assume. So that means you can have the indices from 0 until 99. Initially, each one of them just points to now. Nothing has been stored yet, initially. Okay? So now we have also a counter over here, number of entries. Initially, simply 0. Okay? So there are two purposes for this counter over here. First of all, it tells you the number of entries so far. Okay? That's number one. It tells you exactly how many. And the number two is, it tells you if you want to store a new entry, that is the index you should go into. I'll illustrate that. So the next available slot to save a new entry. Okay, let's see how we do the first one. First entry to insert, we want to insert an entry with 1 and D. Okay, what I can do is, let me just copy this maybe. Okay, the first one, I'm going to put it here. The first one, let's see, the key is going to be 1, so I'll put 1 here, and the value is going to be D, so I'll put D here. Let's create an entry objects, right? And now, how should I put it? Because the current value for a number of entries is simply 0. So I'm going to say m.entries at position 0 is assigned to whatever this new entry is, right? So how do you do that? Well, I just do a link like this. That's how I do it. After that, I should also increment the counter from 0 to 1, meaning that the next element to store, they should be stored in index 1. Okay, let's do just one more and then I'll show you animation to save your time. How do we insert the second one? The second one over here is going to be 25 and C. Again, we simply, first of all, create a new entry object accordingly over here, and then we'll put over here 25 and C over here. Thank you. And then what we'll do is current value is 1. So that means we should really store at position 1, like this. After that, we should also increment the counter value from 1 to 2. Okay, just keep going. Okay, now let's speed up the process over here. Okay, let me go back to the slides. Let's see exactly how things will work. Initially, nothing has been stored, so NOE is simply just 0. After the first one, NOE has been incremented to 1. After inserting the second one, NOE becomes 2, 3, 4, 5, 6, 7. Okay, so that's how we insert the 7 entries in the table. Okay, any question about this? It's actually quite a quick review of how the pattern works for your lab test 1 this afternoon. Hopefully you're comfortable with that. All right. Okay, so now let's have a quick look of the Java code, and then I do have some questions for you to see how bad this can be at the runtime. Okay, question, go ahead. No, it doesn't. I'm just saying this pattern over here using a one-dimensional array. That's, yeah. No, there's no hashing, don't worry. All right, let's go back here. So this is how we define each entry over here. Let's say each entry has a key as a value. Let's say key is simply integer, and value is simply string, okay? And then we have a constructor here, simply initialize the key and the value. Nothing surprising, okay? You can also generate the getters and setters using Eclipse. I showed you previously in the class. Let's talk about this class over here. Let's just call it array map. We simply try to implement a map using a single array. So how do we do that? Now let's see this. Again, should be surprising to you. We define the maximum capacity we assume, let's say 100, up to 100 entries. Entry array, also number of entries counter. Okay, and then that's how you initialize the entry to be with size 100, and also return the size, and also how you put it, right? Nothing surprising. What's more important is the next method. Let's now see some tests very quickly. Of course, if you try to write a test to test the functionality for the array map, initially the size should be 0. And then after adding 7 entries in the order I just showed you, so now the size should be 7. We've got 7 entries so far. And now, let's say we want to support an accessor method called get. How does get do? It's basically like a search. Given a key value, which can be one of the values over here, you can see it can be 1, can be 25, can be 3, any of the key values, we want to return the corresponding entry objects. Let me just make it more vivid for you. If I say m.get, let's say 25, okay? In this case, I want to return the entry objects that has the key value 25. We do have it, which is over here. So I'm going to return the reference to this object over here. That's the method we're going to write together. Okay? Let's see what's the best we can do based on what we have known so far. Okay, and of course, if you just simply want to pass a non-existing key, like a 31, which doesn't exist among all the 7 entries we have inserted, you just return null. Okay, as easy as that. Let's try to program this get method here. Okay, so given the key value over here, how can we locate where the entry is? Yes, question? Yes, basically in this case, we support array map class, and where we got an array of entries, right? So now each entry has a key as a value. Basically for this method over here, given a key, we want to return the associated value, right?
So if we accidentally wrote like the actual value back, so it wouldn't work, right?
So say it again, what do you mean?
Like our value for the entries, like a string, if we accidentally wrote like a string like A in the argument, it wouldn't work, right?
No, it wouldn't even compile. What you're asking is, what if I say m.get, I simply rather than passing an integer, I pass maybe A as a string. You wouldn't even compile. String is not integer, right? Okay, let's think about what we can do to support this get method. What can you do? What should I write? Can a single if then else statement work? No, what should I do? I need a loop, right? Do I need a nested loop? No, right? I don't need a nested loop. Just go from 0 until number of entries, right? That's all I gotta do. Okay? Why don't we have a look? I have a single loop, not nested. I would say starting from 0 until NOE minus 1. For example, you can see that over here, if I only got 2 entries in the map, I only have to go until index 1, which is exactly number of entries, which is 2 minus 1, right? That's the idea. Okay, and then for each one of them, we simply get an entry for the current one we're looking at, and also we get a key. And then we do an if statement here. We say if k is exactly equal to the key we are looking for, then we can return a value. And then we just return. Okay? That's the get method. And if we can reach this point to get out of the loop, that means we haven't found the key. Just return null. Okay? Any question about this naive implementation here? It's not that naive. It's actually correct. But we're going to criticize about it. Question? Yes, before I ask you.
Get key method customized? Like, did you make it?
Yes, the get method, yeah, we just make it, right? We just write it ourselves.
No, get key.
Get key, what do you mean get key? Oh, yes, it is. The question was, there's a get key method over here. So now you can see E is of type entry, right? Remember in the previous slides, I said for the entry class, we got key and value. As I said, you can also support the getters and setters over here, right? That's something that's up to you. It's very easy to implement. Okay, so now let me ask you a question over here. Let's go very slowly. Okay, let's say this is the order of the array. Okay, so the first entry at index 0 is 1D, and 1 is the key, D is the value. The second entry at index 1 is 25C, and etc. We only get 7 entries. Okay, 7 entries over here. And if I want to look for, let's say, let me try to warm you up over here. Now, I want to know how efficient it is to say m.get key value 1. How efficient is that? No? Why? It is efficient. Okay, how about let me define what I mean by efficient. What about we say the way we measure efficiency is by seeing how many iterations you need in order to return from the method. How about that? Okay. Now for this particular key value and for this particular map layout, how efficient is that? When I say m.get 1. 1 iteration, because you can see the first entry there at index 0 is already 1D. Right? We found it right away. Okay? That's good. Now, let's compare another existing key, search, 1 iteration. What about m.get 7? Is it less efficient or more efficient? It's less efficient, right? So now in this case, you can see 7 appears exactly at the end of the store entries over here. You will take just more iterations to get there. How many? 7, right? Good. Okay, so far so good. That's just a warm-up. Let's try to make the case a little bit more general. Let's consider that the whole array of size 100 are completely filled up. We got exactly 100 entries. 100. Now, if I just make it very general for you, I would just say any k value, any integer value. So now, if we already filled up all the array with 100 entries. Now, given a k value over here, what can be the worst case? Best case is just one iteration. What about worst case? 100 iterations. I agree with you. That's pretty good. Let's try to be a little bit more extreme, which is also realistic. What about we got 10 to the 6, a million entries in the array? What's the worst case? You got a million iterations to do in the worst case. It could be that the entries is right at the end of the array, which means you have to go all the way to the end. That's one way. Or It could be that the key you're searching for, it simply doesn't exist. In that case, you still have to go all the way to the end to find out the key doesn't exist, right? So in either case, it's a worst case. So now this will give you some intuition why this solution over here is not very efficient. Because it does the performance, the worst case performance for this particular get method here depends on how large the input array you're talking about. If the size of the array is very big, then the performance can be completely worsened, to its full size. Okay, make it a little bit more mathematical. We say that it's linear. Okay, you know what a linear function is, right? Back in math, for example, when I say linear, in this case, you can think about I'm talking about y, the worst case, the worst case. Okay, y is equal to just x. Okay, that's a linear function, don't you agree? In this case, you can think about this is more like the number of iterations. What about x? X is more like m dot, oh actually, let me put it this way. This is going to be number of store entries. So it's completely linear. So we deserve something that's even better than linear. Okay? Again, linear hopefully just gives out intuition. We'll talk about different classes of mathematical function for your running time when we talk about maybe a little bit later. Okay. After this, let's now see how things can be improved. A much faster and correct solution will be needed. In this case, we can move on to hashing. Okay? Hashing can drastically improve the performance. Okay? Let's see how things might work. Okay, so now what I will do is I'll give you some intuition about how things might work altogether. Okay, just before you see that, let me just open a new page over here. Okay, that's it. So let's understand this concept over here, and everything else on Wednesday we'll just be going over some Java code and some implementation issues. Okay, but that's the most important slide for today, for the hashing. Okay, so now let's talk about the idea for hashing over here. Okay, we know that, remember what I said before. Given an array, for example, let me just call it A. Given an array, if I can give you some integer value over here, it can be A0, A1, or A2, doesn't matter, right? As soon as I give you the index, to really get access to that particular element is very efficient, just by calculating the address, right? We said that already just a few minutes ago. So the idea about improving the search about a get, we just said before, was to think about something like this. Okay? Let's just go over the concept very quickly. We would like to say, every time when you have, let me say this, let me just tell you what conceptually this really means. Let me just put it here. So what we had before, okay, let me just give you an idea over here. Conceptually, this is what we like to have. You can see M is an array map. I'm going to write something that wouldn't compile, but that tells you the intuition. N dot entry, let me use different color here. N dot entries is an array. We know that if we can somehow give an integer index, that'll be extremely efficient. But what about we just give something like this? Let's say I want to look for this particular key value, 25. First of all, would it compile? For this case, over here. M dot entry is 25. Okay, in this case, it will compile, but is that a correct implementation? It wouldn't be, because you can see a slot at index 25 is simply null. Okay, but the idea is, if it would be possible to say, so this 25 over here is a key, but not the correct index to look up. But it's not correct yet. So the idea about hashing is, given any key, let's say just for integer, given any key, we have a way to turn this key into an index into the array. And then, given that index of the array, we can go right away to the hash table, the array. Okay? Let's just see conceptually how that works. And then we just use about 5 minutes, and then we'll continue on Wednesday. Let me give you one example right away. Okay? So the key over here that we talk about is simply some integer. Okay? So the keys, you got plenty of example here. So the key can be 1, 25, 3, 14, 6, 39, and 7. So these values are integers, true, but they cannot be used directly as indices into the array. Just not correct. Okay? So now the idea is we're going to define a process called hashing. Okay? We're going to somehow turn these integer keys into integer indices. And those indices can be used directly into the array. So what do I mean? Okay, let's try that together. Okay? What I will do is I will say, let's say I have an array like that, and the array has exactly 11 slots. Okay, I'm going to store these 7 entries. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let's say this is the array I'm going to use. Okay, I'm not talking about 100 anymore, just for this array of size 11. And now, can we just agree on a formula? I'll tell you the formula right away. The way I'm going to define the hashing is by using a function. And the function goes like this. If I'm given a key value here, I'm simply going to calculate the corresponding so-called hash value by the key value, which is integer, modulo 11. Okay, that's what I'm going to do. Okay, now let's see how things might work. For example, let's see this. Let's try the first one. If I got a key value being 1, what should be the hash code for that?
0.
Are you sure? 0? Well, whatever the key value it is, modulo 11, right? 1 modulo 11 will give me 1. Right? Agree? So what does that mean? That means as soon as I calculate what the hash code is, I should store this particular entry, like a 1 and D, at index 1. Okay? So I'll just put an entry over here, entry, and then I'll put 1 and also D. Okay? That's how I store it. Let's see the second one. What about the 25 over here? 25, what's a hash code? Modulo 11, 3. I agree. That's 3. That means we're going to store the corresponding entry at index 3. I'll just do 2 examples for now. Okay, and then that's going to be an entry, and then we're going to have 3 and then 25. So far we stored 2 entries, okay? One thing to know, you can see it in the diagram over here. So the index into the array is not a key itself. It's a hash code of the key, right? It's actually the modulo of the key, okay? And then whatever we store over there is going to be, it can be the entry. So let's see how would the search improve. So now let's say I want to now re-implement the get method. Let's say, remember the get method looks like this. So string, and then get, integer, and the key. Okay? Now, how do I implement that? I don't need a loop anymore, do I? Because I know that the way I store the entries into the array is simply by turning the key value into some hash code, which is used as the index, and then stored it over there. And now, if I want to retrieve it, why don't I just return the corresponding position? Okay? For example, I'll write it down first, and then we'll see see some example. So what I can do is I can simply say return over here, and then this is the array we are using internally, array A over here, and then the formula we apply was like this: key modulo 11. Just return that. Let's run just the two examples we just saw, okay? So now, how do I say, let's say this is our new version, which is, I claim to be more efficient. If you just look at the code structure, it should be more efficient. There's no loop, right? And the computation for modulo is also very efficient, just a primitive calculation. So now if I say m.get, I want to get the key, the entry for key value 1 versus m.get also for key value 3. Let's see each one of them. How does this execute? Well, if you look at that over here, you can see 1 is the key value over here, right? Key 1. What I should do is I should really go into calculating this integer expression here, which will be 1 modulo 11, which will be 1. That will be a valid index, the hash code. And then I will use 1 as the index into A, which is exactly this index over here. That's how I find this entry. You can see there's no more loop, because the way I store this entry into the array is by applying this particular formula as the index. So the way I retrieve it is by basically applying the same formula again. Okay, let's do one more example. How about here? m.get 3, right? 3 over here, again, we cannot use it directly because you can see we cannot use it directly, so you put 3 here, okay, 3, and then we got 3 modulo 11, which will give you 3. That tells us we should go to index 3, and then get this one here. Question? I might know what you've tried to ask, but go ahead.
But don't you get the same if you do?
Without the modulo?
If you do 3 modulo 11, 14 modulo 11, it's 3.
Good. So it's a very good question. So the question was, according to this formula over here, it is possible to get the same hash code from different keys. For example, let's say 3 modulo 11 is 3. 14 modulo 11 is also 3. You're absolutely right. So this is something called collision in the case of hashing, which in realistic example, when you got so many entries, is unavoidable. Yes, it's possible. But doesn't really destroy the purpose for hashing. As long as the degree of hashing of the collision is not so high, you're still fine. Okay. Okay, guys. Any question about this small example over here? I'm gonna. Okay, question here before I. Yeah. So we say it again. You mean when we have collision, how do you know which one to get? Exactly. Okay. Let me just have a quick answer to this, and then we are done. How about this? So let's say let me pick, let's say 3 and also 14, for example, right? We know that 3 should be stored in index 3, and also 14 modulo 11 will also give you 3. That means should also be stored over here. Basically, in this case, because of collision, what you have is the actual diagram should look something like this. It's going to be pointing to a list of entries. Okay, so it's going to be basically something like this, like a list over here, and the first entry is the 3 and 25, and the second entry is the 14 and maybe 3 and C. Let's say 14 and Z over here. So back to your question, how do we tell? Basically, in this case, you're going to go through the list again using a loop, and then to see which key is equal to the key you're looking for. That's something we'll carry on maybe on Wednesday. Okay, I'll see you today in the lab test.